Hey, the funny thing about life is you could actually do 5 AP questions for a video and forget to turn the camera on. So I'm going to do these problems again. But, if you hear a little impatience in my voice, it's because I've already done these first 5 problems for AP Review 6. Hi, welcome to AP Review 6, rates in and rates out. Rate at which people enter the auditorium for a rock concert is given by R. R is the rate in, and doors open, no one is in the auditorium. The amount of people in the auditorium at time equal to 0 is 0, and the doors are open from 0 to 2 hours. Okay, how many people are in the auditorium when the concert begins? Well, there are no people leaving, there are only people entering, so I'm going to integrate that rate of people entering from 0 to 2 to find the number of people in the concert at time equal to 2. And when I do this, I get that 980 people showed up. Now, how did I do that? Well, I pulled out my calculator, I typed R of t in, and I did F in with R of t from 0 to 2. I'm not going to take the time to show that calculation. That was in the last video that didn't get actually recorded. Instead, I'm going to assume that you can type this integral into your calculator and get 980 people in line in the auditorium, at t equals 2 hours. Okay, B. Then they say find the time at which the rate at which people is a maximum. So I want to know when the rate is a maximum. That means I want r prime equal to 0. This is the rate function, and the rate will have a max when r prime is equal to 0. So I can use a calculator. It's not that hard to take this derivative of r and get that r prime would be 2760 t minus 2025 t squared. And if I set r prime equal to 0, I can factor out a t and say 0 equals t 2760 minus 2025t. And so I get t equals 0 and t equals 2760 divided by 2025. And this turns out to be approximately 1.3629 hours. Okay, so I've got r prime, I've got 0, I've got 2, and I've got 1.3629. And if I check values, like if I plug in a 1 into r prime, this number is bigger than that number, and so I get a positive. And if I plug in 1.5, which I did in the first video, I got a negative number here, and so I see the maximum line length is at, the rate is a maximum at 1.363 hours. Do we have to justify that? Yes, justify your answer. So I'm going to say that R is a max at t equals 1.363 hours because to the left of t equals 1.363, r prime is greater than 0, and to the right of t equals 1.363, r prime is less than 0. Okay, there's part B. Part C says the total wait time for all the people in the auditorium is found by adding the time that each person waits, starting at the time the person enters the auditorium and entering when the concert begins. The function W models total wait time, phew, for all the people. the derivative of w prime, equals 2 minus t times r of t. There's w prime, and they want us to find w of 2 minus w of 1. Well, this is the derivative of that, and so can't I just do w of 2 minus w of 1 equals the integral from 1 to 2 of w prime dt. I can do this on my calculator. I don't have to worry about knowing either of these because I just want to find this expression, and that's just going to be this straight integral. So when I integrate there, I end up with 387.5 hours. These are hours. Okay, that's the total wait time for all the people waiting. Total wait time. Now, if I want in part C, on average, how long does a person wait, I'm thinking about T. I'm thinking about the average time per person as being that 387. Oh no, no. I want the integral from 0 to 2 of w prime divided by the 980 people and waiting in line. So this is kind of an average value, except the average value here would be 1 over 2 minus 0, and I want this. I want the total wait time not divided by the number of hours, but divided by the number of people, right? So I'm going to do this integral divided by 980, the number of people in the auditorium, to find out how long they all waited. And I come up with 0.76 hours waited on average per person. Okay, there's part D for number 1. Let's take a look at number 2. Number 2 says, concert tickets sold for 9 hours. The number of people waiting in line is modeled by twice differentiable function. So L equals the rate in on 0 to 9. And we're given this in a table. So we're probably going to do some kind of RAM at some point. Various times. Use the data to estimate the rate at which people enter the line at 5:30 at 5.5. Well, they want L prime of 5.5, except they want me to approximate that. And I can approximate that with L of 7 minus L of 4 over 7 minus 4. And when I do that computation, I get 150 minus 126 over 3, or 8 people per hour at 5:30 p.m. Okay, there's part A. I'm sorry, yes, part A. Part B says use the trapezoid sum with 3 subintervals to estimate the average number of people waiting in line during the first 4 hours. So this is an average value. I need 1 over 4 minus 0 integral of L from 0 to 4 dt. But to do this part, they want me to use the trapezoid sum. So I've got that 1/4. Now my trapezoid sum, 1/2. And because the subinterval widths are not the same, of course, 1 plus base 1, 120 plus 156 plus 3 minus 1 times 156 plus 176 plus 4 minus 3 times 176 plus 126. Close parentheses, close brackets. And so there's the average value. This turns out to be 155.25 people in line each hour on average. Okay. Bum. I think you could get away with leaving this, but I feel a little more comfortable leaving that. And this is a calculated question. Okay, part C. Part C says on 0 to 9, the fewest number of times at which L prime must equal 0. Well, L prime equals 0 when L has a max or a min. And let's notice here, our values seem to be increasing and then decreasing. So if I went from increasing to decreasing, I must have a max. And then I was decreasing, but then I'm increasing. And I don't know if this is the low point or the low point is in between here or the low point is in between here. I just know I'm increasing, then decreasing, then increasing, then decreasing. So again, I'm increasing, decreasing, increasing, decreasing. So it looks like I'd have 3 times when L prime equals 0 because L goes from increasing to decreasing or decreasing to increasing 3 times on 0 to 9. Okay, there's part C. What about part D? Part D says the rate at which tickets are sold, ooh, there's a rate out of the line is 550 t e to the negative t over 2 tickets per hour. How many tickets were sold by 3 p.m. to the nearest number? Oh, well, this isn't asking for the line length. This is just asking for the number sold. And so if I integrate R from, it said, how many were sold by 3 p.m., so 0 to 3, I should be good to go. There shouldn't be anything else to this. And I get 972.784, and we want to the nearest whole number, and that's approximately 973 tickets sold by 3 p.m. Okay, that's problem number 2. Let's take a look at problem number 3. Here's a traditional rate in, rate out problem. The tank contains an amount, 125 gallons of heating oil at time equal to 0. And in these rate in, rate out problems, we can do a generic sort of a of t minus a of 0 equals the integral from 0 to t of the rate in minus the rate out dx. And so we'll add this initial amount to this integral to have an amount at certain times. But for that's going to be very common. But for part A, it just says how much heating oil was pumped into the tank on 0 to 12. Well, our rate in this problem is h. So if I integrate h from 0 to 12, I'll get the number of gallons that are in the tank, or pumped into the tank from 0 to 12. And when I did that on my calculator, I got 70.571 gallons pumped in on 0 to 12 hours. Okay, part B. Part B says, is the level of heating oil in the tank rising or falling at time equal to 6? Well, I want to think about this level a second. So let's imagine that this is an h function and that this is an r function. And if this is the rate in and this is the rate out, and the rate in is above the rate out at a certain time, then the amount would be increasing. But if the rate out is above the rate in, then the amount in the tank would be decreasing. And we want to know, is the amount increasing or decreasing at time equal to 6? And so I want to consider h minus r. H of 6 minus r of 6 to say something about a prime of 6. A prime of 6. So let's take a look at this. And in fact, we could go back up here and say, hey, I want to know the rate of change in the amount. So we'll take the derivative up here. And so the derivative of this is a prime. The derivative of a number is 0. And the derivative of this integral is just going to be h minus r. And so that's where this comes from. And now I want the amount at 6. So that's just going to be h of 6 minus r of 6. Okay? So when I do this on my calculator, I get negative 2.924. And we can say that since h of 6 minus r of 6 is less than 0, the level in the tank is decreasing at time equals 6 hours. Okay, there's part B. What about part C? Part C says how many gallons of heating oil are in the tank at time equal to 12. Well, there's our amount function. A of 0 equals the integral from 0 to 12 of h minus r dt. So the amount at 12 is going to be the amount at 0 plus the integral from 0 to 12 of h minus r. So we said originally there were 125 gallons, and I add that to this integral. You can do this as two separate integrals if you like. Generally what I like doing in problems like this is typing h into y1, so 2 plus 10 divided by 1 plus ln of x plus 1, close parentheses, and then here I'll type in r as 12 sine of x squared divided by 47. Because I have a trig thing here, I'm going to check my mode is in radians. Good. Back to y equals, and then here I want y1 minus y2. I'm going to turn these other functions off, and I'm just going to be considering this one for now. And so I go over here and I say, hey, let's integrate y3 comma x comma 0 comma 12, and then don't forget to add the 125 to that. Oh, lots of thinking time. Thank you, calculator, for doing all the thinking. And so I get negative 2.974, and so A of 12 equals 122.026 gallons at time equal to 12 in the tank. Okay, that's part C. What's part D say to us? At what time is the volume of the heating oil in the tank the least? Okay, so I want to know about A prime equal to 0, and we said before that A prime was h minus r, and so I want to know when h minus r equals 0. Well, conveniently, I've got this function here called h minus r. So if I change my viewing window to be 0 to 12, I just hit graph. I can graph, or thank you, calculator, for graphing for me, this h minus r function. I can see that h minus r is equal to 0 at two different places, and those places turn out to be a prime 0, 4.790, and 11.318, and don't forget the endpoints. So how did I find that? I did second calculate 0 to find that point there on my graph. Okay, so now I'm going to do a candidates test. I need a of 0, I need a of 4.79, I need a of 11.318, and I need a of 12. Conveniently, I know that there are 122.026 gallons at 12 and 125 at 0. So I'm just going to find these other ones. And how do I find these amounts? Well, I go back to my amount function, and I plug in the times here. So I'm going to plug in a 4.79 here and a 4.79 here. So I need to integrate from 0 to 4.79 and add 125. So let's go back to this, plus 125, and change that time to 4. Second insert 790. Okay, enter. And I get 149.407. And then if I check going out to 11.318, delete, bump. Ooh, it does take a while. I get 120.738. And so we're looking for the least amount in the tank is least at t equals 11.318 according to the candidates test. You know, you could say you've got a plus, a minus, a plus here. You could say, hey, I've got a min here, but I also have a min here. And so the question is, how do I know which is the smallest of these mins? And notice that this value here is 122, which is in fact less than this min over here at 125. So even though this is low, this is even lower. Yeah, so I really do need to do the candidates test to make the determine when is the least. Please make the candidates test your friend. Okay, that was problem number 3. Let's take a look at problem number 4. Problem number 4 has for us a graph to look at of two functions. We've got a rate in function, this curvy thing, f, and we've got a rate out function, that's this piecewise linear thing. And so I see here that the rate out is greater than the rate in, which means the amount must be decreasing. Here, the rate in is above the rate out, so the amount in the tank is increasing. Here, the rate out is above the amount in, so again, the amount in the tank is decreasing, but over here, the rate in is above the rate out, and so the amount in the tank would be increasing again. Okay, so we're going to be thinking about that same a of t minus a of 0 equals the integral of rate in minus rate out dx 0 to t. This is going to show up in almost all of these rate in, rate out problems. So I'd be thinking about this, but often not the first question, which should be easy and straightforward. It says how many gallons enter the tank on 0 to 7. So the amount entering, I have a rate for that, and if I integrate that rate, I get the amount entering the tank, and that was if I integrate f from 0 to 7. So if I integrate f from 0 to 7, I get 8263.807. I read the question again. It says round your answer to the nearest gallon. And so this is approximately 8264 gallons enter on 0 to 7. Okay, part B. On 0 to 7, find the intervals at which the amount of water in the tank is decreasing. Give a reason for each answer. Oh, well, we just talked about that, didn't we? We said when G was above F, that was the rate out was greater than the rate in, the amount would be decreasing. So for parts B, we'll say decreasing, amount is decreasing on 0 to, conveniently they gave me those points of intersection as 1.617, union, and then the next time G is above F is from 3 to 5.076, and my reason here would be because G is greater than F. Yeah, that's all I need to say for amount is decreasing. Okay, part C. Part C says on 0 to 7, when is the amount of water in the tank the greatest? To the nearest gallon, compute the amount of water at those times. Well, this is another candidates test. And I see a bunch of values here. A of 0, A of 1.617, A of 3, A of 5.076, and A of 7. So I need to find these values. This is going to be a little interesting because the g function isn't always the same. So here, for example, I can say a of 0 plus the integral from 0 to 3 of the rate in minus the rate out, which is 250. But when I get down here, this is a different rate out function, but I need to still take into account all the amount that came before. And so I think I want to change this not to be a of 0 anymore, but to be a of 3 plus the integral from 3 to 5.076 of f minus 2000 dt. And so this one would be a of 3 plus the integral from 3 to 7 of f minus 2000 dt. Okay, so let's see what we get for these different values. I'm going to type in my f function here, 100 x squared sine square root of x. And then here we have just 250. And there's y1 minus y2. Okay, guess I don't need to turn these off. And we know at time equal to 0 there are 5,000 gallons. Okay, so math, integrate, y3, comma, x, comma, 0, comma, 1.617. Don't forget to add those 5,000 gallons. Okay, and we get 4719.222, and they wanted us to round to the nearest gallon, so I'm just going to say 4719. I repeat the process for 3, so second entry. All I have to do is change this to be 3.000. And I get, impatient, waiting for the calculator to do all this amazing work that I would otherwise complain about, I get 5126.590, so 5127 gallons. Well, that's more than I started with. And now I have to switch my g function to be 2000. So let's go back here and change this to be 2000. And then our integral, we're no longer integrating from 0, we're integrating from 3 to 5.076 plus that 5,000. So my calculator chugs away and comes up with 3890 gallons. And then finally the amount at time equal to 7. I'm integrating out to 7 now. Oh no, these are the amounts at 0, not the amounts at 3. My bad. Let me fix that. The amount at 3 we said was 5126.590. Okay, so our new amount here is 4513.8. Oh, no, that's 7. Goodness me, going too fast, people. 4513.805 is 4514 gallons. Okay, and then what about at time equal to 5.076? Let's edit this once more. 5.076, and we're adding the amount at 3. Good. And this comes back as 4016.880 or 4017 gallons. Okay, so that's my gallons, and then what about my max? Well, that's what we wanted, wasn't it? When is the amount in the tank the greatest? At time equal to 3, amount in tank is greatest, 5.1 approximately 2.7 gallons, according to the candidates test. I'm interested to see if there's a candidates test on the pandemic here, because candidates test takes a little while to compute all those values. Okay, let's see, what's next? Problem number 5. Problem number 5, a tank at Camp Newton holds 1,200 gallons at time equal to 0. That sounds familiar. There's a rate in, and there's a rate out. And so I know at some point in this problem I'm going to be doing a of t minus a of 0 equals the integral from 0 to t of w minus r dx. Okay, but maybe not in part A. Is the amount in tank increasing or decreasing at time equal to 15? So for that I want a prime, and if I take the derivative of this I get a prime. The derivative of a number is 0, and the derivative of this integral is just going to be w minus r. I want to know what a prime of 15 is, and so that's just going to be w of 15 minus r of 15. So I'm going to type w into y1, and I'm going to type r into y2. y1, 95 square root t. Be careful typing in sine squared. Sine, see the parenthesis? Sine of x divided by 6, close 2 parentheses, squared, and then 275. Ooh, another sine squared. Sine of x divided by 3, close two parentheses, squared. And again, my y3 is y1 minus y2, y1 minus y2. Okay, so I don't want to integrate here. I just want to go to my table and type in a 15, and I see that y3, come on, y3 is negative. This is less than 0, so the amount is decreasing at time equal to 15 hours. Okay, and the why or why not, that's the why or why not. That's all I need to say, because the amount in is greater than the amount out. I mean, I guess I could say W of 15 is greater than R of 15. That would also be an appropriate justification. Part B, to the nearest whole number, how many gallons are in the tank at time equal to 18? Here's our amount function. A of 18 equals A of 0 plus the integral from 0 to 18 of W minus R dt. So we've got 1,200 gallons here. To add to that integral, I want to integrate, integrate y3, comma x, comma 0, comma 18, and don't forget to add those 1,200 gallons. Then I get still thinking. I get 1309.788, and they say here to the nearest whole number. So 1309.788 is approximately 1310 gallons at t equals 18. Okay, that's part B. Let's take a look at part C. Part C says, at what time is the amount in the tank an absolute min? Show the work that leads to your conclusion. Well, this means I need to do a candidates test. So let's take a look at our candidates. We've got, I don't know where my candidates are. I need to graph Y3. So the others are turned on. Let's turn them off, so that I'm only looking at Y3 from 0 to how many hours? 18, 0 to 18 hours. And I'm looking for 0, so negative 1 to 1 is fine. Okay, so we're going to graph. We're going to find some critical points. Second, calculate 0. 1, 2, 3, 4, 5, 6, between 6 and 7. Okay. That went too far. Okay, I'm to the left, I'm to the right, I hit enter, then I get t equals 6.4, 9, 4, and because I went from minus to plus there, minus plus 6.494, this is 0, we got this other time, and then 18. Second, calculate 0. Values are coming down finally. Oops. positive to negative, and I get 12.975. Okay, and so I want to consider A of 0, I want to consider A of 6.494, I want to consider A of 12.975, and I want to consider A of 18. So we already found the amount at 18, but sadly I didn't record that value. Maybe it's still over here. 0 to 18 plus 1,200 gallons. That looks like 1310 approximately. And here we had 1,200. So now let's do our amount function calculation again. But this time we're going to go to second insert 6.494. And I get some wait time. Five to 5.242. And then I want to repeat this process one more time by doing second entry, 12.975, 0 to 12.975 plus the 1,200. Good. Candidates testing is always something I do for absolute min and absolute max. Yeah, equals 1697 gallons. And what are we looking for here? The amount of water in the tank is an absolute minimum. Amount in tank is an absolute minimum, 525 gallons at T equals 6.49. I have 495 in my notes. 495 in my notes, so maybe there was a rounding issue, and I didn't round carefully enough. According to the candidates test. Okay, so there's part C, and wait, there's more. There's a part D. So T greater than 18, no water is being pumped in. The water continues to be removed until the tank is empty. Let K be the amount of time it takes for the tank to become empty. So we found out that, I can't believe I just erased all those numbers. I really did just erase all those numbers, didn't I? Oh my god. Let's see what I can get back. A of 0, A of 6.494, A of 12.975, and A of 18. Okay, this was 1,200. This was 525. This was, because they want to the nearest gallon, 1697. And I need to do 18 again. And you may say, why do you need to use 18 again? Well, because I need the amount that's in the tank at the starting time for part D. Dough. I can't believe I dropped this out. Okay. Come on, little calculator. 1310. Oh, yes. Okay, and that's approximately. Great. So let's take that one. And K is the time of the tank. Write but do not solve an integral equation that could be used to find the value of K. So I could say I have 13 10 gallons to figure out, and we're going from 18 to K, and we're just doing R of T. Yeah, that's my integral there for number 7. Um, for number, I'm sorry, number 5. Number 5, part D. We could make it more complicated. Like we could say the integral from 18 to K of R of T equals the integral from 0 to 18 of W minus R plus the initial amount. But all of this is that amount at 18. And so I just assume use the amount at 18, which is why I went back to find it. I think this is a much tidier answer, right? But do not evaluate an integral. Okay. So problem number 6. Let's see what problem number 6 says. Problem number 6, the storm washed away a beach, causing the edge of the water to get closer to the road. The rate at which the distance between the road and the edge of the water is changing during the storm is modeled by f of t. And f equals this funky function plus cosine t minus 3. You know, if you find functions like this interesting, you might want to consider mathematical modeling. Mathematical modeling is something that we do to get a sense of this. Yeah, to get a sense of this. Okay, so at what time is the distance between the road and the edge of the water at the end of the storm? So if I integrate f from 0 to how long is the storm? 5 hours dt. That's going to be the edge at 5 minus the edge at 0. We know the edge at 0 is 35, so 35 plus 0 to 5 integral f of t dt. And that I get on my calculator 26.495 meters. Okay, there's part A. Part B. Part B says, using correct units, interpret the value of f prime of 4 equals 1.007. Well, I know that the units on f are meters per hour, and f prime would be meters per hour over hours, right? Because this is a change in f over a change in time. So meters per hour is what I would be getting here. In fact, I could just slide that next to that. And what do they ask? What does this mean? Yes, what does this mean? Well, the distance between the road and water is changing by 1.007 meters per hour every hour. This is that one. This is the stuff on top. And that's all I need to say. Okay, that was part B. Part C says, at which time during the 5-hour storm is the distance between the road and the water decreasing most rapidly? I'm looking for decreasing most rapidly. So I know that e of t minus e of 0 equals the integral from 0 to t of f dx. This is the distance. This is the change in the distance. The rate of change in the distance, e prime, is f. But I'm looking for changing most rapidly. I'm wondering when this function has a max. And so I want e double prime or f prime equal to 0. So how can I find that? Well, again, I can, I guess I could graph this. But really, I think, why don't I do candidates test again? So if I consider, hello, little graphing calculator. If I consider here this function, my function here is f prime. Oh, f prime is given. F prime is 1 divided by 2 square root of x minus sine of x. That's f prime. Okay, and I want to know when f prime equals 0. So I'm going to graph f prime on 0 to 5. F prime equals 0 at t equals this point and this point. Second, calculate 0. Bump, bump, bump. And I get 2.840. And then I find second calculate 0, this other one over here. Oops. Well, I didn't change the value, so I need to do that again. Second, calculate intersect, enter, enter, enter. And I get t equals 0.798. Those are my 2 times point. Whoa, those are very different times than the times in my notes. Oh? I got this one, but not that one. That's very interesting. That's very interesting. I'm just going to check that again. My function, 1 over 2 square root minus sine. I'm still in radians, good. And I'm graphing, and I'm doing second calculate 0. I want to be to the left. I want to be to the right. And I hit enter. Ah, there we go. I don't know what happened before. I'm a silly Billy. 6, 6, 2. Okay, so I've got some values. I want e of 0. I want e of 0.662. I want e of 2.84. And I want e of 5. Okay, so what was the distance at time equal to 0? That was, oh, but these are f primes. Yeah, so I want change. So I want f evaluated at these points. Okay, so let's get our f function, not our f prime function typed in here. And our f function, the original function was square root of x plus cosine x, don't forget to close that parentheses, minus 3. Okay, I go, where did I type that? I didn't type that. That's very interesting. Okay, square root of x, close parentheses, plus cosine x, close parentheses, minus 3. And I go over to my table, and I type in 0, and I get negative 2, and I type in 0.662, and I get negative 1.398. Huh. And I type in 2.84, and I get negative 2.27. And I type in a 5, and I get negative 0.4803. Okay, and so decreasing most rapidly, that's the most negative number, and that's this one. This is decreasing most rapidly at this time. Most rapidly at t equals 2.84 hours according to the candidate's test. Okay, so that's part C, but wait, there's more. Part D. Part D says that there is a recovery vehicle. Ooh, I like a recovery vehicle. The recovery vehicle starts pumping sand back onto the beach at GOP meters per day, where P is the number of days since pumping began. Write an equation involving an integral expression whose solution would give the number of days the sand must be pumped in order to restore the original distance between the road and the edge of the water. Okay, well, so if I integrate this g of p function from 0 to x days, that's got to be equal to how much distance was lost. And the amount that we lost was f of t from 0 to 5. I think that's correct. Let's integrate f of t. This one's f. So if I do f of t, that's y2 from 0 to 5 plus 35 yes. Plus 35. I get 26.495 equals 0 to x of g of p dp. I think I like that one. I'll have to think about that one. Okay, that was 6D. 6D. Take a picture of that one and just check that. Okay, 7. Let's take a look at 7. 2 more problems to get through here. Well, 7. So 7 says oil is leaking from a pipeline, forms a slick, so the volume of the slick is changing at 2,000 cubic centimeters per minute. The units, cubic centimeters per minute, help me realize that this was a change in volume with respect to time. The oil slick forms a cylindrical shape for convenience. Again, you could have wackier shapes up here, more realistic if you took a math modeling class. Okay, what do we know? At the instant the radius of the oil slick is 100, r equals 100. The height is 0.5. The radius dr dt equals 2.5 centimeters per minute. At the instant, what is the rate of change in height? dh dt. Okay, so this is a chapter 5 related rates problem. We know that volume is pi r squared h. They've given us dv dt and dr dt, and we're looking for dh dt. So I have to take the derivative over here. But unlike a lot of the related rates problems where we had a helping equation to get rid of this and get everything in terms of one variable, here we don't. Here we have to use the product rule. So pi r squared dh dt plus the derivative of this would be 2 pi r dr dt times h. And now we can plug in what we know. We know 2,000, we know pi, we know 100 squared. dh dt is what we're looking for, plus 2 pi times 100 times 2.5 times 0.5. And so when I solve for dh dt, I end up with 2,000 minus 250 pi divided by 100 squared pi. And I get 0.039, and those would be centimeters per minute. So it's not getting very high, very fast. It's getting much wider, much faster. Okay, there's part A, a related rates problem. Part B, a recovery device arrives on the scene, not unlike the recovery device in the last problem, and begins removing oil. The rate at which oil is removed is given by R of t. Find the time when the oil slick reaches its maximum. Well, so what I'm thinking about here is thinking that our rate in is dv dt, and our rate out is this thing that they're calling r. And so the amount is the amount at time equal to 0 plus the integral from 0 to t of dv dt minus r dx. That's what I'm thinking about for this problem. And so that's going to be this is our constant 2,000 minus r. And so this is with calculator. Good. So A, and do I know how big at time equal? Oh, at time equal to 0, the oil slick is 0. It hasn't grown yet. So I've just got the integral from 0 to t of 2000 minus 400 square root of t dt. Okay. That's perfect. Now find when the oil slick reaches a maximum. So I want to know when a prime equals 0, and that's when 2000 minus 400 square root of t. Oops, these can't be the same as that. T equals 0. So 5 equals square root of t, 25 equals t. I get t equals 25. And if I look at my A prime sign chart, I have 0. And do I go forever? The recovery vehicle just works forever, or at least until, well, so I'm going to put my 25 down there. And if I plug in a 1 here, I get a positive. And if I plug in something that I can easily take the square root of, like 100, as a test value over here, I'll get 10 times 400 is 4,000, so that's a minus. And so max at 25, and the units here are minutes. Okay, do I need to write my justification sentence? Yes, justify your answer. Okay, so, um, oil slick is at a max at t equals 25 minutes because to the left of t equals 25, a prime is greater than 0, and to the right of t equals 25, a prime is less than 0. Remember, you have to define an a function or an a prime function in order to use that justification. Okay, so that was part B, the recovery vehicle. Part C. Let's take a look at part C. By the time the recovery vehicle has begun to remove oil, there's 60,000 cubic centimeters have already leaked. Write but do not evaluate an integral expression involving that gives the amount of oil found in part B. Oh, so we want to know the amount of oil at 25. Okay, so we have 60,000 at, we have 60,000 when the recovery vehicle arrived. And, oh, so this would be 25 minutes after recovery vehicle arrives. 60,000 equals our integral from 0 to 25 of 2000 minus 400 root x. This is the change. This is the initial amount. That's not an equals. Oh, I know what I'm doing here. Okay. So I'm saying v of 25 minus v of 0 equals this. And so v of 25, I add v of 0, or 60,000, to both sides. I get 0 to 25 of 2,000 minus 400 square root of x dx. Okay, so that's what the recovery vehicle does, and that's the original amount. I add those two together, and I should end up with this. Great. Okay, and this would be volume in centimeters cubed. So there's part C for number 7, and all we have to do is number 8 now. Number 8. Number 8 says the intersection of Thomasville, Oregon, cars turn left at 60 square root of t sine squared t over 3. Yeah, I feel like we saw a function not unlike that a little while ago. Over the time from 0 to 18. Okay. The graph of L is shown above. Okay. To the nearest whole number, total number of cars turning left on 0 to 18. Well, that's just the integral from 0 to 18 of L of t dt. And when I do that on my calculator, I get 1657.8. And it says to the nearest whole number, so approximately 1658 cars turn left on 0 to 18. Okay, please just don't write 1658, but actually give it a context. We've been working on that all year. B. B says traffic engineers consider turn restrictions when L is greater than 150 cars per hour. Well, I see here L does go above 150 cars per hour. Find all the values for t where L is greater than or equal to 150. And then compute the average value of L over that time interval. Okay, so I'm going to graph L of t, and I'm going to do second calculate intersect with the line 150, just like I showed here. I'm going to graph 150, I'm going to graph L of t, I'm going to find these points of intersection. I found them to be at t equals to 12.428 and t equals 16.122. Now we want to know the average value of L over this interval. Okay, so that's 1 over 16.122 minus 12.428 integral 12.428 to 16.122 L of t dt. And when I computed that on my calculator, I got 199.417 cars turn left per hour on average from 12.428 to 16.122 hours. And that's certainly above the 150. Okay, and part C, finally, traffic engineers will install a signal if there's a 2-hour interval during which the product of the total number of cars turning left, I feel like I need to really write something down now. The product of the cars turning left, 0 to t dx, times the total number of oncoming cars, which is 500, is greater than or equal to 200,000. If there's a 2-hour window where this is true. Okay, so let's think about that. If I divide both sides by 500, I have 0 to t of L dx greater than or equal to 400. Okay. So when is L? So this is a 2-hour interval. If I divide by 2, I get 200 for a 1-hour interval. So I'm wondering if L is greater than 200 from when. So I'm going to graph L of t, but this time I'm going to graph 200, and I can see, yep, between these two times, L is greater than 200, and that happens between t equal to 13253 and t equal to 15.323 hours. This is a little more than 2 hours, and during that 2 hours, the left turners are more than 200, so the total of the product of left turners and the oncoming traffic would be greater than, so they do need to install a signal. Okay, and there's AP Review 6. I hope this was helpful for you.